Let's begin by reviewing the theorem that we proved at the end of the last lecture. So what we showed is that if you have an analytic function f on a domain D and a point in the image of the domain D by f, so you have z naught in D mapping to w naught in f of D, then for some small disk around w naught, and so for any w within a distance delta, say, of w naught, that point is in the image of f, right? So in other words, any point in this disk, in this small disk around w naught, is also in the image of f. And in fact, it's the case that that small disk around w naught, it's actually in the image of a small disk around z naught. So it suffices to stay close to, so you can stay close to z naught, and those points end up hitting the points close to w naught. So you don't have to go far away from z naught to find points that hit the points close to w naught, is basically the point. And in this small disk around z naught, the number of zeros of f of z minus w, in other words, the number of solutions of f of z equals w in this small disk, counting the multiplicity, is equal to the order of the zero z naught of f of z minus w naught. So we know that z naught is going to w naught, but z naught could be going to w naught more than once, quote unquote, in the sense that the order of that zero of f of z minus w naught could be bigger than 1. But in any case, whatever that order is, that's the number of solutions of the equation f of z minus w for those close by w to w naught. So basically, you sort of have the same number of solutions to f of z equals w as to f of z equals w naught if you constrain yourself to look at appropriately small neighborhoods of z naught and w naught. And we discussed that heuristically the reason you expect this is because f of z minus w naught, if you expand in a power series and then throw away the higher order terms because you're going to think about z being close to z naught, that this difference is basically just the simple polynomial a sub m times z minus z naught to the m. And so it's basically, it's approximated by the leading term of the power series. And the polynomial mapping, so if you center your domain and your range at z naught and w naught, you can think about that analogous to the polynomial mapping. Z goes to a constant times z to the m, taking 0 to 0. So near 0, that polynomial mapping has the properties in the conclusion, right? So it maps a disk around 0 from the domain to a disk around around 0 in the range, and has the property that, well, actually that mapping is m to 1 away from 0. So 0 is a sort of 0 of order m, and every point that's close to 0 in the range is getting hit m times. The function, the inverse image of a point that's not 0 has m elements in it. And just a recall that the proof idea is to use Rouché's theorem. So what you do is you compare the number of zeros of f of z minus w naught, which you know for z near z naught. So if you bring z close enough to z naught, then z naught is the only zero, because you have isolated zeros of analytic functions. So z naught will be the only zero of f of z minus w naught. And then using Rouché's theorem, as long as w is close enough to w naught, f of z minus w will have the same number of zeros as f of z minus w naught. Okay, and so that's the outline of the proof. The basic takeaway of this theorem that you should note is that what it's saying is that the image of, or in particular one thing it's saying is that the image f of d is an open set. So I should refer you to the picture up here. If you have z naught going to w naught, then you can put a little disk around w naught that's in blue there, which is also contained in the image. Right? So any point you can put a disk around it which is contained in the set f of d, and that's exactly the definition of a set being open. If you can put a little disk around any point in the set and that disk is still contained in the set. So one thing so what we're saying here is that the image of any domain by an analytic function is open. And you can contrast this with real differentiable functions, even the simplest kind of real differentiable functions. For example, polynomials. So a real polynomial doesn't have to take an open set to an open set. So f of x being x squared, if you think about what f does to the interval -1 to 1, it kind of folds it over on itself around 0. And so you get this half open interval. It's not open at 0, right? You can't put any small interval whatsoever around 0 is going to have points in the complement of that f of d. So that is not an open set. Okay, so complex functions are, in this sense, different than real differentiable functions. One corollary of this theorem is something that might be a bit familiar from calculus. So in calculus, if you have a function and you're looking at a point where the derivative is not equal to 0, so f prime at, say, x naught is not equal to 0, then intuitively that tells you that the function is locally increasing or decreasing, right? So in this picture it's increasing. You could have something like this, where in the neighborhood of this point is f prime. So f prime here is greater than 0, f prime here less than 0, your function's locally decreasing. And so if you look close enough to x naught, since you have increasing and decreasing, this function is going to be 1 to 1 in a neighborhood of x naught. So you have x naught down here. There's going to be a little interval around x naught where your function is strictly increasing. And in this picture you'd have a little interval around x naught where your function is strictly decreasing. And intuitively speaking, that seems plausible. It turns out you actually need to assume that f prime at x naught is continuous. So f prime, you have to assume that f prime is continuous at x naught in order for that to be true. And so basically, this function being 1 to 1 in this little neighborhood here, when that maps up, that tells you that locally you have an inverse function for this function f. And so basically, if you have f prime at x naught not equal to 0 and f prime continuous at x naught, then that implies that f is locally invertible. Locally invertible. And so the same thing is true here for complex differentiable functions. And we don't have to assume the continuity, of course, in this case, because the continuity of f prime automatically follows from its existence, right? Because we have power series expansion, as we've talked about to death. So that's the content of the next theorem. So the statement is that if the derivative of an analytic function at a point in a domain is not equal to 0, then f is 1 to 1 in a small neighborhood of that point z naught. So if you restrict to that neighborhood, then f has a local inverse. And the proof is to use the previous theorem. So since f prime of z naught does not equal 0, we have that f of z near z naught equals a naught plus a1 times z minus z naught plus ... where and that's near z naught, where a1 is not equal to 0. And so a1 not equal to 0 is equivalent to f prime at z0 not equal to 0. So what this implies is that so f of z minus a0, so a0 is just f of z0, right? That has a 0 of order 1. So by the open mapping theorem, we are guaranteed a disk d around a0 of radius delta, and a disk around z0 of small radius, such that for every w in the disk around a0, there is exactly one z. And so remember, so basically the solutions for f of z minus w, the number of solutions I counted with multiplicity is the same as the number of solutions to f of z minus a0, right? But the order of that 0 is 1, so there's only one solution to this, and so there must only be one solution to that as well. So there is exactly one z satisfying f of z equals w in the disk around z0 of radius r. So in other words, f is 1-to-1 in, so if we look at the inverse image of the disk around a0 of radius delta, and so that's everything that maps to those w's in that disk, and then we intersect it with the disk around z0 of radius r, so that's the inverse image, and then it intersects with that disk, then there's only going to be one thing in that set which is mapping to a given w, right? So in other words, f is 1-to-1 in that set, and that set is open. So the disk here is open, and the inverse image of an open set by a continuous function is open. So we just have the intersection of two open sets, and that is going to be an open set. And that completes the proof of the theorem there. So one thing I'll remark is that, in fact, the local inverse of f above is also an analytic function, and we won't prove this. And this, so this local inverse, it satisfies, so this local inverse G, it satisfies that the derivative of G at some, so the derivative of G, well, it's defined, right, since it's an inverse, it's defined on points in the image of f. So the derivative of G at f of z is the it's 1 over the derivative of f at z, which is a formula you might be familiar with from calculus. And this is easy to prove from the chain rule. So this is easy to prove from G composed with F equals the identity map equals the identity. Yeah, equals Z. So assuming that that this function G is analytic, then you can apply the chain rule to this composition formula and derive this formula here. But the slightly more tricky bit is to prove that G is differentiable in the first place. All right, so we won't go through that. It's a little bit tedious. So I just want to round out our local picture here of what our analytic function is doing. So basically, remember, the whole way we started talking about this is by looking at the power series for f of z minus w naught near z naught, and the leading term is a polynomial, so that polynomial approximates. So the picture of that polynomial, how that polynomial maps, approximates the picture of our analytic function near z naught. And again, just here's the picture of how that polynomial maps. It takes these wedges, which are an nth of the circle. So 2 pi over m is the angle for the wedge, and each of those wedges gets mapped onto the full circle in the range there. So you see, like, the inverse image of a point, one single point on the right is m points on the left. And so that's where we got our intuition that the number of solutions to f of z minus w, and so the number of solutions to this equation should be the same as the number of solutions to f of z minus w naught equals 0, right? And this was just m here, right? So we successfully predicted that as long as everything's close to z naught and w naught, that the number of solutions here should also be m. But so an interesting question arises, though. We're counting those solutions including multiplicity, right? So while in this picture of up here of the constant times z to the m, the function is truly m to 1 away from 0, right? There really are m distinct points in the pre-image of the red point on the right. But it could be that since that's only an approximation of the true picture of our function, it could be that there's not truly m different points in the pre-image of a point for our function. So the basic question is f of z truly m to 1 close to but not at the point z naught? And so this would give us somewhat more precise information about how the function is mapping near z naught, not just that counting the multiplicity, we have m solutions to an f of z minus w equals 0, but that we truly have m distinct solutions to that. That would be stronger information. And it turns out that the answer to this question is yes. And so that's the content of the next theorem. The statement of the theorem is that at a critical point z naught of an analytic function with domain D, so in other words, a critical point, just as in calculus, is where f prime at z naught is equal to 0. Our function is m to 1 in a small disk around z naught, with the exception of the point z naught itself. So so you read that the punctured disk around z naught at radius r. Which is really an annulus, so it's the annulus around z naught with inner radius 0 and outer radius r. So in that disk, our function is going to be m to 1, where m is the order of the 0 of f of z minus f of z naught at z naught. Okay, so that's just again, the intuition is just it's telling you that your function is acting very much like the polynomial given by the leading term of f of z minus f of z naught. And here's the proof. The proof is that, so near z naught, so use the fact that we have a critical point first, f of z equals z naught plus, well, there is no degree 1 term because the derivative is 0 at z naught. So what we're going to have is that this is going to start at, say, at a sub m times z minus z naught to the m plus dot dot dot, where this am here, so am where, or well, let me, before I say that, let me just finish this little computation. So this equals z naught plus z minus z naught to the m times, well, after I factor that out, I just have a power series, and so that's going to define an analytic function g of z. Right, so here, where so in this case, our m is at least 2, so where m is bigger than or equal to 2. And in g, so g, the first term in the power series for g is this am, so g at z naught is not equal to 0. So I guess I'll say g is not 0 at z naught, and g is analytic. The basic outline of the proof is what we're going to do is write g of z as let me see, as h of z to the m. So we're going to show that we can take the mth root of g of z, and that's still an analytic function h of z. So there's an analytic function h of z such that when you raise it to the m, you get g of z. And then with that, f of z is going to be z naught plus z minus z naught times g of z to the m. Right, and then we can call this L of z. So f of z is z naught plus L of z to the m. And the thing about L of z is that because g of z has a non-zero leading term, of order 0 in its power series, L of z, and so L of z starts with am times z minus z naught, right, plus dot dot dot, where this am is not equal to 0. That's the same am as up here in f. And so L prime at z naught is equal to am, which is not equal to 0. Right, so this L has a non-zero derivative at z naught, and so it's locally invertible. So locally, what we can do, so we're going to have so L inverse exists near z naught. And so then what we can do is for any, so if we have f of z equals w, right, an equation like that, we want to say that this has exactly m solutions. Well, this is just equivalent to L of z to the m equals w minus z naught. So if we take the mth root here, right, this fixed complex number has m roots, right, m distinct roots. So so L of z, that equals like zeta 1 through zeta m, where those zetas are mth roots of w minus z naught. And then, well, because L inverse exists, then we can solve z is L inverse of zeta 1 through L inverse of zeta m. Right. So that tells us that there's exactly m solutions, and those are m different solutions because the zeta 1 through zeta m are different, and so that tells us that your function is m to 1 locally. So what we have to do is write that out. And the first thing we need to say is that g has an mth root, right? So we claim there is an analytic h of z such that h of z to the m is equal to g of z. And let's say which is defined in any sufficiently small disk around z0. And so g of z itself came from the power series for f. G of z is just defined by a power series in a disk, so in that disk we'll be able to find this mth root function h of z for g of z. And the key to this is just that we can find an analytic logarithm for this g of z function. So the first thing we need to say is that because g of z is not equal to 0 at z0, it's not equal to 0 by continuity. If we look in some sufficiently small disk around z0, g is not going to be 0. So by continuity of g and g at z0 not equal to 0, there is a small disk around z0 such that g of z is not equal to 0. So now we have a function which doesn't vanish in a disk, and a disk is simply connected. So what we can do is you can find an analytic logarithm for this function g. So since a disk is simply connected, there is an analytic function, let's say k of z, defined in it such that e to the k of z is equal to g of z. Okay, and then all we have to do, so basically what we're going to do is take this e to the k of z and just write that as e to the 1 over m k of z times m, and that's e to the 1 over m k of z to the m. Right, and so this is going to be our function h of z here. So then define h of z to be e to the 1 over m times k of z. Okay, so which clearly satisfies h of z to the m equals g of z, right? So that function does exactly what we were looking for. So it's basically our ability to find analytic logarithms of non-vanishing functions in simply connected sets that we use here to take an mth root coherently. Because there's problems with mth roots because they're ambiguous, but we can do that unambiguously here. So continuing with f of z is z0 plus z minus z0 to the m times g of z, and g of z is h of z to the m. And so this is z0 plus z minus z0 h of z, all that to the m. And now defining L of z to be z minus z naught to the h of z, we find that f of z is z naught plus L of z to the m. So the next thing is that, so what we want to say is that L is locally invertible, so that we can solve an equation like f of z equals w with it. And in order to do that, we want to check that the derivative of L at z naught is not equal to 0 and use the inverse function theorem. So we can compute that L prime at z naught by the chain rule, right? Use the fact that this is z minus z naught times h of z, and that's our definition of that there. Well, yeah, right here. So that is just going to be the same as h is just h at z naught. So which is not equal to 0 since h at z naught to the m is equal to g of z naught, and g of z naught is not equal to 0. You refer back up here in the proof. Okay, so h of z naught can't be 0. Thus, L is locally invertible by the inverse function theorem, I just realized something embarrassing. I've been putting z naught in a variety of places, so I've been starting the series for f around z naught with the leading term z naught, but that's not correct. It should say a naught. So I'll have to just go back and edit that from a number of places. So I need to fill in a naught for all of those. So that's a naught, a naught, a naught, a naught, and a naught. Okay. So we have this local inverse for this L, and so we can restrict, so in a small enough disk of radius r, say around z naught, it will be the case that f of z equals a naught has only the solution z naught with multiplicity m, and L has an inverse. Thus, for any z in the punctured disk, so z in z naught radius r, but not z not equal to z naught, the solutions for the equation f of z equals w are given by, so f of z, that's equal to a naught plus L of z to the m equals w, and that's L of z to the m equals w minus a naught. You see, since z is not z naught, this w here, so f of z equals w, that w, since z is not z naught, cannot be a naught, right? Because the only solutions, so this is not equal to, w is not equal to a naught, right? So that's why we wanted to make sure our disk is small enough that f of z equals a naught has only z naught as a solution. That's isolated zeros of an analytic function again. So this is not equal to 0, right? So I guess it's a given by solutions of, so since w minus a naught is not 0, it has mth roots, mth roots. Say psi 1 through psi m. So thus L of z equals psi 1 dot 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 L of z equals psi m. And so right, and those are all distinct. So the psi's are all distinct. So the psi I are all distinct. And therefore z equals L inverse of psi 1 through L inverse of psi m are m distinct solutions, are the m distinct solutions to f of z equals w in the punctured disk. Okay, and that's the proof of that. So intuitively, what this theorem tells you is that this perfect picture of constant times z to the m, which approximates what your function looks like around z naught and w naught, is really a pretty good representation of the actual picture. So the actual picture, would probably look something like here's your w naught, and you were to look at something like this. So I'll kind of draw the same picture again, centered at w naught. Then the inverse image of that, it wouldn't be a disk, but it would be pretty close to a disk around z naught. And so you'd have z naught here, and then you would have like wedges that all map to that disk. So m different wedges, each mapping to the full disk, and maybe the wedges would look a little like wavier or something. So that'd be kind of the idea, and that red point, right? You have one of those in each of the wedges there. So that would kind of be how the mapping looks. Each of those wedge regions maps onto that whole disk, and there's m of those wedge regions like that. So that's kind of the local picture. So this is the local picture of an analytic function. And that's at a critical point, function at a critical point. So the open mapping theorem led to the inverse function theorem, and that led to that theorem we just talked about that tells you what an analytic function looks like around a critical point. But if we go back to the open mapping theorem, there's another famous corollary of that result, and that's called the maximum modulus principle. Something else just occurred to me. I realized I didn't say that our analytic function we're talking about in all of this is not a constant function. So that's an important, so I'll just say f is non-constant throughout. Okay, so we're talking about non-constant analytic functions. Of course, a constant function is going to map a domain to a non-open set. So a single point is not an open set. So that's an obvious sort of counterexample there. So we're talking about non-constant analytic functions. So the maximum modulus principle says that if you have a non-constant analytic function on a domain D, then looking at the modulus of our analytic function, so that's a real valued function, that can't have a local maximum at any point in the domain. So that means that that it can't be the case that in some small disk around our point z0 that the modulus of f at z0 is bigger than or equal to the modulus of f for all of the z in that small disk. So intuitively, why this is the case is that if you have your domain D and your point z0, if this was a local max of the modulus, then there would be a disk around z0 such that the image of that disk, so if you look at f of z, so f of z0, right, that has to be further out from the origin. So let's put the origin in the picture, and so there's going to be in the image. So here's the origin. And that f of z is going to be further out than all of the other z's in that little disk. So if we color a disk red here, then the image would kind of have to look like, so f of z0, like that length, if we draw a disk of that radius, a little piece of a disk of the radius norm f of z0, then all of the points around z0 there have to map closer to the origin than f of z0, so have to be inside that disk of the. So our image points would kind of look like, they have to fall inside the disk like that. But that means that the image of this disk, so that would mean that f of this little disk around z0 of radius r is not going to be open, right? So this is not open, because if we put a little disk around f of z0, right, that's going to contain points that are not in the red part. So the image of that little red disk. So that little red disk is a domain, so its image is supposed to be open under f according to the open mapping theorem. But it clearly is not, because any small disk is going to have points further out from the origin than norm of f of z0, and so that's going to contradict open mapping. So proof. Suppose that the norm of f of z0 is bigger than or equal to the norm of f of z for all z in some disk around z0, say of radius r. So since since the disk around z0 of radius r is a domain, f of this disk around z0 of radius r must be open. By the open mapping theorem. So there is a small disk, around f of z0, so say of radius delta, which is contained in the image, so f of d z0 r. But the problem is that this small disk, it contains points in it further away from the origin than f of z0, right? But so the norm of those points, right? So there's got to be some like zeta in here such that the distance of zeta from the origin is strictly bigger than f of z naught. But the zeta is supposed to be f of some z within this disk, and that contradicts the given inequality. Right? So that's the basic point there. To make that precise, so to get points further away from the origin than f of z naught in this disk, just go a distance of, say, delta over 2 further out in the direction determined by f of z naught. But let's say zeta equal to f of z naught plus delta times f of z naught over the norm of f of z naught. This is in the disk around f of z naught of radius delta, and the length of zeta, that is clearly equal to, this should be delta over 2. So this is equal to the length of f of z naught plus delta over 2, and that's greater than the norm of f of z. But zeta equals f of z for some z. There's some z in the disk around z naught of radius r. So we have f of z is greater than, or norm of f of z is greater than norm of f of z naught. And that's a contradiction. A contradiction. Okay, and so that's the proof. And so you can think of this by contrast with real functions as usual. So in an open set, your complex differentiable function, you can have a local maximum in the sense of the norm of f can't have a local maximum. But of course, in Calc 1, right, you're used to talking about local maxes of functions. So you talk about them all day long in Calc 1. So this is very much different than the situation in calculus. As a corollary, we can say something about the real and the imaginary parts of an analytic function. So a corollary is that the real and imaginary parts of a non-constant analytic f in a domain cannot have a local max or min. And the proof of that, so as the proof, so write f as u plus iv, so u and v are the real and the imaginary parts. Then the norm of e to the f, so e to the f is an analytic function, and the norm of that is e to the u, while the norm of e to the minus if, so if we multiply f by minus I, then the real part of that is now v, and so the norm of e to the v plus I, whatever, that is e to the v. So a local max of u or v would give a local max of the norm of e to the f and norm of e to the minus if, and e to the f, e to the minus if are non-constant analytic functions. So this can't happen by the maximum modulus principle. So this can't happen by the maximum modulus principle. And then similarly, norm e to the minus f equals e to the minus u, and norm e to the if equals e to the minus v, and local mins of u and v. And so the mins, when you take the negative of them, would become local maxes, right? So the e to the minus u and e to the minus v would have local maxes. Similarly, that and local mins of u and v correspond to local maxes of e to the minus u and e to the minus v. So an analogous argument applies. Okay, and so that tells us about so the real imaginary parts of an analytic function. They're special kinds of functions of two variables. Right? So they're real valued functions of two variables, but a real valued function of two variables can have a local max or a min. I mean, it's easy, you can just picture a graph of it. But these functions are special. They don't ever have local maxes or mins. And now a corollary of this. A corollary of this is that if the domain D of a non-constant analytic function f is bounded, so that is you could just say that you can put your domain, you can enclose your domain in a big disk or in a big square in the plane. So it doesn't go off to infinity in any direction. You can contain it in a finite portion of the complex plane. If that's bounded, then norm f and the real part of f and the imaginary part of f take their maximums on the boundary. So I guess you could say on boundary of D. And the proof is just that so the proof is that the closed bounded set, so closed and bounded set, D union its boundary. So if you add in the boundary points for D, we now have a closed set. On the closed and bounded set there, those three functions, they have to obtain a maximum. And that's a theorem of analysis that I've mentioned a number of times that we're just sort of accepting as given. So the closed and bounded set, so I guess I should say, maybe I'll revise the beginning of that sentence. So on the closed and bounded set, the continuous functions, so it only matters that they're continuous. The continuous functions norm f, real part of f, and imaginary part of f must achieve a maximum, achieve their maximums, but by the maximum modulus principle, it cannot happen for any point in D, for any point in D. So it must occur on D, on the boundary of D. So it must So they must occur. So any maximum whatsoever. There could be multiple different points that achieve the maximum. So any max must occur on the boundary of D. And the same would apply for the minimums of the real part of f and the imaginary part of f. We can't say anything about the minimum of the function norm of f, right? Because the minimum could well be 0 inside, right? So the minimum of the norm of f would be 0 when our function has zeros, right? And our function is allowed to have zeros in the interior of a domain. There's no problem with that. Possibly the last thing we're going to talk about is the Schwarz Lemma. And the Schwarz Lemma, you can roughly think of it as, well, it tells you something about the rigidity of analytic functions. So let me put down the statement here. So the Schwarz Lemma applies in the following situation. So suppose you have an analytic function defined on the unit disk around 0, that f maps the unit disk basically to itself, possibly taking interior points to the boundary. So in other words, you can say this as just the norm of f of z is less than or equal to 1 for all z in the disk, and that f fixes the origin. Okay, so the origin doesn't move, and all of the points are just moving around inside the disk itself. And so that's sort of the geometric picture. Then, in fact, the norm of f of z is less than or equal to z for all z in the disk. And so what you can read this as saying is that if you, so here's your disk of radius 1. So here's your unit disk. And let's say you take a z inside here at radius r, small r. Right, so there's a z. That your function f has to take that smaller disk of radius r to itself as well. Right, so your function is doing something like, okay, so I'll have to draw the disk again. Right, so the image of the whole disk, it has to fit in the disk like this. So that's the red. So that's that red disk there. Let's say this inner one in blue. And so let me redraw that disk over here. Then that blue disk, that has to go inside of that blue disk. Okay, so basically what the Schwarz Lemma says is that with these hypotheses, so just mapping the disk to itself and fixing 0, that every sub-disk that's centered around 0 has to also be mapped into itself, right? So you can't have these sub-disks, right? So it could be possible a priori that the map is taking the big red disk and shrinking that down a little bit in total, but that it's expanding some of the interior parts, right? So it's sort of like contracting the outside but expanding on the inside. But that is not the case. So just fixing 0 and having this function from the disk to itself means that all of the smaller subdisks around 0 are being sent to themselves as well. And furthermore, so continuing reading the theorem, if f of z, the norm of f of z equals the norm of z for even a single z, right? So here, so let's say our f of z, so z here, if f of z, right, if it goes to f of z, which has the same norm as z, so let's suppose, yeah, so, right, I guess I should have, okay, sorry, let me take this back here. It's all right, I'll draw f of z over here, right, so you have f of z on that at the same norm as z itself, then in fact this whole map is just a rotation, right? So if you have even one point z, which you could which you could rotate into its image, right? So you can sort of think about it that way. Like this z, since z and f of z have the same norm, you could rotate z into its image f of z, right? If you can even do that for a single z, then in fact the whole map has to just be a rigid rotation, right? So that's what this this unit length complex number lambda, right? So multiplication by unit length complex number lambda doesn't scale, right? It just multiplies everything's norm by 1, so no scaling, and then just rotates by the angle of that complex number. Okay, so these so functions from a disk to itself are very rigid as far as if they fix the center of the disk. So as far as complex in the complex realm. So it might help before we look at the proof to look at an example in the real world. So again, this situation described in the Schwarz Lemma is very different from real variables. So the analog would be like a real differentiable function which maps the unit interval, so from -1 to 1 to itself. And so I'll kind of draw the situation. So you have -1 to 1, -1 to 1. So you got -1, 1, -1, 1. And so to show in the real realm we can defy this situation, right? So basically the Schwarz Lemma says that so the Schwarz Lemma in the real world would say, like, if you preserved the interval from -1 to 1, so if you map that to itself, then you would have to preserve every sub-interval. But we do not have to do that at all. So here's an example. So I draw the 45-degree line through here. I can use that to illustrate a function. So I'll draw something like that. And so the key point is that it has to be that it's going to be below the line here and above the line on the right hand side. So basically the fact that so that would take an interval, so an interval from -r to r. The interval -r to r on the y-axis is like, right, so you follow -r up to this point on the so follow -r up to this point here on the line r to that point there. So that would be this interval from -r to r on the y-axis. But our function itself, where that maps, is it maps to the green point there, right? So green point, green point. So the actual map takes that interval from -r to r to an interval which is bigger than the interval from -r to r. Right, so even though it maps -1 to 1, the interval -1 to 1 to the interval -1 to 1, it does not map the interval -r to r to -r to r, and that's true for any. So that was just an arbitrary r that I picked. So that's true for any r whatsoever, which is between 0 and 1 for this function. And you could even write down. It's not too hard to write down that the function f of x equals 2x over 1 plus x squared. That has a graph like this. So you're basically just sort of taking that straight line x and you're exaggerating it a little bit. So 1 plus x squared. This is less than 2, right? So that's less than 2 for x between -1 and 1, and so 2 divided by that, well, that's going to be bigger than 1, right? So this whole fraction here is bigger than 1, and it's right. So that's going to be sort of expanding the graph of x just out a little bit, which is kind of what we see in the picture there. Okay, so and this is of course a real differentiable function. So real differentiable functions don't have to do anything like what the Schwarz Lemma is saying here. Oh, I should have noted that that 0 goes to 0 for this function, of course, right? So f of 0 equals 0. So we have it fixing 0, but it's expanding every subinterval, even though it takes the full interval -1 to 1 to itself. The proof of this is not really obvious, and the first people who knew about Schwarz's lemma, they used sort of heavier hitting machinery heavier machinery to prove this, and then it was finally this proof I'm about to give is kind of the canonical one, which is the simplest, but it's a little bit clever. So it starts from here. So since f of 0 equals 0, right, if we expand the power series for f around 0, it would start with a m z to the m plus blah blah blah, where am is not equal to 0 and m is bigger than 0. Right, so what we can do is, so that means that we can consider f of z over z. So that function will be an analytic function, right? Okay, so that's basically the first line of the proof. So since f of 0 equals 0, g of z, which is f of z over z, is analytic on the unit disk. And it satisfies, that the norm of g, which is equal to the norm of f over the norm of z, right? The norm of f, since f, the image of f is contained in the disk, this is less than or equal to, that numerator is less than or equal to 1, and then we just leave the denominator alone there. So now the maximum modulus principle tells us something interesting. So if I look for z in the disk around 0 of some radius r between 0 and 1, let me call this delta sub r. So if I look at a z in there, this norm of g, so I know norm of g is less than or equal to 1 over norm z, right? And this estimate here gets worse as z gets closer to 0, right? So the further you go into the interior of our little disk, the worse this estimate gets. But that's backwards from the maximum modulus principle, right? So the maximum modulus principle tells us that the max of norm g of z, that actually has to occur on the boundary of this little disk of radius r. So even though we have this bad estimate here, which is going to infinity as z goes to 0, by the maximum modulus principle, right? So what we know is that, for example, if we take z on the boundary of this disk, that for those z we have g of z less than or equal to 1 over r, right? But since that holds on the boundary, that has to hold throughout the entire disk, right? Or throughout the entire disk of radius r. So the maximum modulus principle allows us to improve this estimate. So we get this uniform estimate here throughout all of the of that disk. So we say on the closed disk of radius r, norm g obtains its maximum which is no worse than 1 over r from the preceding inequality. So that is on the closure of the disk of radius r, the norm of g of z is less than or equal to 1 over r throughout that entire closed disk. But now we can improve this again because as r gets bigger, this estimate gets better, right? So because r is between 0 and 1, so the closer r gets to 1, the smaller this right-hand side gets, right? But if here's our disk of radius 1, if we take a z that's at norm r, so let's say that this is at distance r here, then Z is in every other disk of a larger radius, right? So if you think about this disk of radius S, Z is in that closed disk of radius S. So what we can say is that the norm of G of that Z is not only less than or equal to 1 over R, it's less than or equal to 1 over S, right? And then we can let S go to 1, and by continuity, we see that the norm of G of Z is less than or equal to, or I guess just properties of limits. We see that G of Z is less than or equal to 1 for that Z, and that applies for any Z in the disk. Okay, so that's the next step of the argument. So for fixed Z in the unit disk, with the norm of Z equal R, then Z is in the closure of the disk, and so G is in the disk around 0, or well, I guess I've just been saying delta. So Z is in delta sub S, the closure of that for all S which are bigger than or equal to R and less than 1. So thus the norm of G of Z is less than or equal to 1 over S for each S such that S is between 0 and 1. And so taking S going to 1, we find that G of Z's norm is less than or equal to 1 for any Z in the disk, right? For any Z in the open disk, the open unit disk. But G is just F over Z, right? So therefore, the norm of F of Z over Z is less than or equal to 1, i.e. the norm of F is less than or equal to the norm of Z for all Z in unit disk. Okay, so so one thing, note that this implies that actually F is a function from the unit disk to just the unit disk. Right, F of Z's norm of F of Z is less than or equal to norm Z. You can't be mapping to the boundary of the disk at all. Okay, and then so we still have to look at the case. So if F of Z, so norm of F of Z equals norm Z were to hold for some Z, then the norm of G at that Z would be equal to 1, would hold. Sorry, I just realized something again. This statement here, we have to say for all Z in the punctured disk here. So, of course, since F of 0 equals 0, we have the norm of F of 0 is equal to the norm of 0. So that's not an interesting condition, or yeah. So we have to be able to allow that condition. So we're talking about the interesting condition is if F of Z's norm equals norm Z for a single Z which is not 0 in the disk there. Yeah, so that allows us to go from, so we're assuming Z is not equal to 0 here in order to go from F of Z to divide by Z there and get to G of Z. And so then, but since 1 is the maximum of norm G, right? So remember we have norm G is less than or equal to 1, and Z is in the interior of the disk, is in the interior of unit disk, the maximum modulus principle, implies that G is identically equal to a constant, lambda, and plugging this in norm G of Z equals 1 gives norm lambda equal 1. So we have f of z over z equals lambda, equivalently f of z equals lambda z, where norm lambda equals 1. Okay, so in this case, our function f is a rotation, pure rotation. All right, so so that gives you some idea of the rigidity of complex functions in contrast to complex differentiable functions in contrast to real differentiable functions. All right, I'm going to stop it there.